Okay, so as we were discussing, there are two types of superconductor, and the first type is the type which we have see so far all discussed about losing superconductivity when you increase the external magnetic field. So the typical graph, if you plot the external magnetic field graph with magnetization, it looks something like this. So this is the external magnetic field H. This is magnetization, which we also denote with minus of M. So array baapre. Magnetization, which is the if in effect inside the material due to the external magnetic field. So the typically how superconductor works, if you keep increasing external magnetic field, the superconductor creates its own magnetic field which is equal and opposite direction. That's why this is minus M. So equal and opposite. So if you keep increasing this value will also keep increasing, which is negative of in the negative direction of this. So the typical graph will look something like this, and at certain value suddenly the external magnetic field wins over the expulsion of magnetic field, which is Masonry effect, and this will suddenly go down, and of course it will go something like this. So this is called type 1 superconductor. So you can start writing. You just give the title type 1 superconductor. The transition from superconducting state to normal state, in the presence of a magnetic field occurs sharply. Transition from a superconducting state to normal state in the presence of magnetic field occurs sharply at the critical value of Hc. So this is 0 and this value particularly is Hc. So sharply at Hc, and field penetrates completely inside the sample, and field means of course external magnetic field and field penetrates completely inside the sample completely inside the sample. Okay, up to critical field strength means this much, up to this much. So for all these values up to the critical field strength, magnetization of the material grows in proportion to the external field. Magnetization of the material grows in proportion to the external field. So this is growing of course in negative direction, but this is growing in proportion to this. Okay. Fine. You should draw this diagram as well. So probably you can again pause this video. I don't have to wait while making the video, just draw this diagram live. Okay, after you drew this diagram, just further few more important points. The examples aluminum and lead. So aluminum and lead. Okay, low values. So this happens, this value is actually very less. So for industrial purposes, for typically this type of superconductors destroy their superconductivity at very low value of Hc. That's why they are not useful for industrial purposes. So just write down this. The superconductivity gets destroyed. Superconductivity gets destroyed at low values. Superconductivity gets destroyed at low values of critical field. Superconductivity gets destroyed at low value of critical field, and hence it cannot be used in producing large magnetic fields. So that's why this type of superconductor are called soft superconductor. They are called soft superconductors. Okay, so this was about type 1 superconductor. Similar way, there are second type of superconductors, and we can directly see in terms of graph. The similar graph I will plot. So for second type of superconductor, of course this much part is same. So this is external magnetic field, this is again minus of m, which is magnetization. So as you keep increasing the external magnetic field, magnetization also will keep increasing. That is pretty much similar, so it will also keep increasing. It should be with 45-degree angle. Anyway, you can forgive my drawing skills because that's not important here. So first of all, those are called hard superconductors because magnetic field required to destroy the superconductivity is very high. Okay, so they have three states. First, the similar behavior what happened for the type 1 superconductor, that when you keep increasing the external field, internal magnetization also keeps increasing, and up to some certain value. Fine. After this, something really interesting happens. After this, what happens? It does not abruptly fall to the zero, but it goes into something like this nature. So this is very interesting, that so you can observe this part is non-linear. It is reducing, but it is not reducing abruptly to zero, and it is reducing non-linearly. So in reality, actually its slope is very slow, and it will go even out of this boat. Okay, so mainly it has three states. First, up to certain value, they call it as, say, give the name HC1. It will the magnetization will increase as you increase external magnetic field. Fine. Even if you keep increasing external magnetic field, now magnetization will slowly keep reducing up to some certain value, up to whatever some certain value, and even above that at particular value they call it HC2, where superconductivity becomes completely zero. So this is again very important thing. Okay, so I evolved this diagram a little bit, so you can directly start writing. Just give the title type 2 superconductor. They are called hard superconductors, and have three states of superconductivity. Okay, first give the title. You are writing anyway this whatever I have explained in the words. First, superconducting state means from here to here. Superconducting state, it occurs up to critical field HC1. Okay, magnetization increases with applied magnetic field. So magnetization increases with applied magnetic field. And next point, magnetic flux is completely expelled from the interior. Magnetic flux is completely expelled from the interior. So this was the state 1. So it has 3 states, as I am saying. This was state 1. Next, mixed state. Mixed state. So this region I am talking about now. You can start writing. From Hc1 to Hc2, from Hc1 to Hc2. This region extends from Hc1 to Hc2. Hc1 from Hc1 to Hc2. At Hc1, flux starts penetrating the material. At Hc1, flux starts penetrating the material. Flux start penetrating the material. So what is happening is flux starts penetrating, but it does not penetrate completely. So if this is the superconductor, so at this point, or say at little bit above Hc1, the field will be able to penetrate a little bit in depth in all direction, from all the direction, but not completely. That is the main difference between type 2 and type 1. Okay. Further line, material is in the mixed state between Hc1 and Hc2. Between Hc1 and Hc2, material is in the mixed state. Material is in the mixed state magnetically. Material is in the mixed state magnetically, but electrically it is still superconductor. But electrically it is still superconductor, and hence Meissner effect is incomplete. And hence Meissner effect is incomplete. Just take a moment if you could understand this point. What do you mean by this line? Mixed state, magnetically it is in the magnetically mixed state, but electrically it is still superconductor. So what happens is magnetic flux penetrates a little bit, not completely. So because it penetrates a little bit, only to that part superconductivity is killed, but still most of the remaining part superconductivity, it is still superconductor. And hence for electric point of view, the because electricity will always flow from the least resistance part, and for those that region which is not, which is still superconductor, will have zero resistance. So even though some part has lost superconductivity, some part has still superconducting properties, and hence electricity will flow from it, from only that region, and it will behave as a proper superconducting property electric point of view, because it will have zero resistance. That was the main point. I hope you understand this. Okay, the next line. They are useful in applications where high magnetic fields are created. They are useful in applications where high magnetic fields are created. Okay. Third, normal state. So third, which is normal state. So from here onwards. So from here onwards, normal state. Normal state. You can also write something like this. Okay. So this is mixed state. Mixed state. Okay. So what happens above? So this is the Hc2, and after this I am talking about. So fine. So normal state, you can just write, it's a one sentence. When a magnetic field exceeds critical field strength Hc2, when magnetic field exceeds critical field strength Hc2, magnetization vanishes completely. Magnetization vanishes completely and material reverts back into normal state. So that's it. This is about type 1 and type 2 superconducting states. Thank you very much. Take care.